If you watched our last episode, and really if you haven't, you should, you now know all about derivatives and how to use them to describe the way an equation is changing. Which means we can now talk about the other main part of calculus, basically the inverse of derivatives, called integrals. Integrals are useful because they also tell you a lot about an equation. If you've plotted an equation on a graph, the integral is equal to the area between the curve and the horizontal axis. Finding an integral is a little less straightforward than finding a derivative, but as with derivatives, there are shortcuts we can use to make things a little easier. We'll even be able to use integrals to talk about how things move, specifically the equation we've been calling the displacement curve, and why it looks the way it does. So let's get started. Say you want to know how high your bedroom window is above the ground outside below, but you don't have anything to measure it with, just a ball, the stopwatch app on your phone, and your impressive knowledge of physics. The force of gravity is what makes the ball fall, so you know that its acceleration is small g, 9.81 meters per second squared downward. But you're trying to find its change in position, how far it falls. We've spent a lot of time talking about the connection between the qualities of motion, position, velocity, and acceleration. But so far, we've been describing that connection in a particular direction. Velocity is the derivative of position, that is, a measure of its change, and acceleration is the derivative of velocity. To figure out how far the ball falls, you need to use the reverse of that connection. Expressed mathematically, that means velocity is the integral of acceleration and position is the integral of velocity. In other words, if you draw these equations on a graph, velocity is equal to the area under the acceleration curve and position is equal to the area under the velocity curve. Finding that area is the tricky part. There are simple ways to find the area of pretty much any shape as long as that shape is made of nothing but straight lines and corners. And when you think about it, a curve is just a set of infinitely tiny lines. So the area under a curve can be divided into a set of infinitely tiny rectangles. Integrals tell you what happens when you divide the area under a curve into those infinitely tiny rectangles. Take the area of each of them and add those areas up. So how do you find that integral? Well, you start by using the fact that integrals are basically the opposite of derivatives. If you know that your velocity is equal to twice time, for example, then you know that's the derivative of the position. So to find the equation of your position, you just have to look for an equation whose derivative is 2t, like x equals t squared, for example. It's kind of a roundabout way of doing things compared to the neat equation we were able to use to find derivatives. But there is no tidy equation that we can use to calculate any integral we want. But hold on, don't panic. As with derivatives, there are shortcuts for finding certain useful ones. For instance, you can take the power rule that we use for derivatives and run it backwards. Basically, you add 1 to the exponent, then divide the variable by that number. So the integral of 2t, which is written like this, becomes t squared. In the same way, the integral of 42t to the power 5 is 7t to the power 6. You can take the trigonometric derivatives that we talked about and do those backwards too. The integral of cosine x is sine x and so on. And the integral of e to the power x is just e to the power x. But there's one complication that we haven't talked about yet. Maybe you've already spotted it. Constants. A constant is basically just a number. It can literally be a number, like 2 or a half or a -4. Or it can be a placeholder for a number like the small g we've been using to represent the acceleration caused by gravity. And constants pose a problem when it comes to integrals because the derivative of a constant is just 0. A derivative is a rate of change after all, so a constant by definition doesn't change, and so we'll always have a derivative of 0, which means that lots of different equations, an infinite number in fact, can all have the same derivative. Like the derivative of t squared is 2t, but you can add any number or a letter representing a number to it, and the derivative will still be 2t. So the derivative of t squared plus 1 is also 2t, and the same is true for t squared minus 7. Which means if you're looking for the integral of an equation like x equals 2t, you have infinite choices, all of which are equally correct. T squared would work, but so would t squared plus 1, or t squared minus 7, or t squared plus 0.256. In these cases, we might know what the shape of the integral should look like on a graph, like whether it's a straight line or how it curves, but we don't know where to put it along the vertical axis. So we need to know what the constant is in order to know where to start drawing its integral. Whatever the constant is equal to, that's where the curve will intersect with the vertical axis. So t squared would intersect at 0, but t squared minus 7 would intersect at minus 7. You get the idea. Mathematicians had to figure out how to get around the problem of having infinite integrals to choose from. So they came up with a way to represent all of them, Just add c at the end of the integral. That c stands for all of the constants that we know we could put there. So if we say that the integral of 2t is t squared plus c, then we're including t squared plus 1, t squared minus 7, and all those other infinite options. Every equation whose derivative is 2t. But sometimes you don't need c at all because you can figure out where your integral is supposed to be on the y-axis, like if you have what's known as the initial value. In the case of a position graph, for instance, the initial value would be where you started out, so you'd know to draw the rest of the graph's shape from there. If you started at the 2 meter mark, say, and you moved 1 meter every second, you'd put the graph here. But if you started at the 4 meter mark, you'd shift up a little. Basically, it gives you the point where your integral intersects the vertical axis, which is the value of c. Let's try it, and at the same time, you might as well figure out the height of your bedroom window. You're standing in your room holding a tennis ball out of the window with your arm resting on the sill. Now you drop the ball and start your stopwatch app at the same time. Turns out that ball takes 1.7 seconds to hit the ground. Like we said earlier, we know the ball's acceleration, 9.81 meters per second squared, and we know the time involved. Somehow we have to get from there to the equation for the ball's position. So first let's find its velocity, the middle step, by taking the integral of its acceleration. Take a look at this graph of the ball's acceleration over time. It's just a flat line, which means it should be pretty easy to find the area between it and the horizontal axis. It's a rectangle, and the area of a rectangle is just its base times height. In this case, the base is t, the amount of time the ball took to fall, and the height is a, the acceleration. So the area between the acceleration graph and the horizontal axis is just a times t. And the integral is a times t plus that constant we add, c. For now we need the c because we know the general shape of the velocity graph. It's a diagonal line slanted in such a way that every second it rises by an amount equal to the acceleration. But we still don't know where to put that line on the vertical axis. Not yet, anyway. Now we could have figured out the integral of the acceleration just as easily by using the power rule. The acceleration a is a constant, but we could also say that it's a times t to the power 0, because anything raised to the power 0 is just 1. So according to the power rule, the integral of acceleration, which is the velocity, would be equal to the acceleration multiplied by time plus c. And that's the same answer we got earlier. Now here's where the initial value comes in. The velocity graph tells you what the velocity is for each moment in time, but we had to add the c because we didn't know where to place it on the vertical axis when time equals 0. So the integral of the acceleration could have just been acceleration times time, or at. But it also could have been at plus 4 or at minus 6. So we could put a c in the integral instead to represent all those options. But we can get rid of that c if we can figure out the velocity when time equals 0, what we've been calling v0. And if we write out our equation with that v0 in it as a placeholder for the velocity when time equals 0, we end up with the full equation for velocity. That should look familiar because it's one of the kinematic equations, the definition of acceleration. Neat how everything works out like that. This equation tells us that the final velocity of our falling tennis ball when it hit the ground was 16.7 meters per second downward. But we aren't done yet. We're looking to link acceleration and position. So we'll need to go one step further by integrating again. There are a couple of different ways we could do it, but let's just use the power rule again. The integral of at is half at squared, and the integral of v0 is just v0 times t. Put them together and you'll end up with this, which is starting to look a whole lot like another kinematic equation, the one we've been calling the displacement curve. Now, what about that c? Well, just like before with the starting velocity, the starting position will tell us where to stick this equation on the vertical axis. So we'll just make c equal to the starting position, which we'll write as x0. And that's our integral, the displacement curve equation, which means that now we have everything we need to figure out how high your window is. The starting velocity is 0 because you just dropped the ball without throwing it. The acceleration is 9.81 meters per second squared, and it took 1.7 seconds to land. And now you have everything there is to know about calculus. No, you don't. As you can probably imagine, we've barely scratched the surface here. There's a reason why it normally takes 2 semesters of university just to cover the basics. And you know, some people spend their whole lives studying this stuff. But at least we've established enough background that when those things do come up in this course, you'll be able to use what we've covered here to talk about them. Today you learned the integrals of the area between an equation on a graph and the horizontal axis. You also learned a few shortcuts to help find them and how to find c using an initial value. Crash Course Physics is produced in association with PBS Digital Studios. You can head over to their channel to check out amazing shows like Shanks FX, Growth Science and PBS Game Show. This episode of Crash Course was filmed in the Dr. Cheryl C. Kinney Crash Course studio with the help of these amazing people, and our equally amazing graphics team is Thought Cafe.